Okay, there's our picture. We want the equation of a plane with a normal vector n through a point defined by a vector r. Here's a picture. Here's a vector r, and here's our normal vector. And this represents our plane. Wherever the normal vector happens to be, this plane is going to be perpendicular to it, meaning every vector in the plane is perpendicular to n. Okay? So if we have two vectors in the plane, we can find a normal vector by taking their cross product, right? Any two vectors in the plane would do that. Okay?
It won't give the same cross product, will it? Just a different magnitude?
Yeah, well, it doesn't matter what the magnitude of n is, because, you know, it just makes no difference. Any normal vector will do to get the equation of a plane. Okay? So if you wanted the equation of a plane and you had two vectors in the plane, you just take their cross product and you get a normal vector. Okay? Or maybe you're just given the normal vector, or maybe the normal vector is the gradient of some function, whatever that is, and that's easy. Okay? And when we see it. So, what's the condition for another point xyz to be in the plane? Now we're going to let P stand for the point x naught, y naught, z naught. R is a vector, x naught, y naught, z naught. We thought, yeah, x naught i plus y naught j plus z naught k, right? And its initial point is 0, so that the terminal point is at the point x naught, y naught, z naught. Okay? It seems like an unnecessary complication, but as I said before, the R vector could be a vector defined by some parameterization of a curve or a surface or whatever, okay? So it's natural to define a point in terms of a position vector. And an R vector usually designates a position vector, as you've seen with the parameterizations we've talked about already, okay? Position vector relative to the origin. Okay, so anyhow, here's our picture. And the bottom line is we've got a point and we've got a normal vector. However we got the normal vector, however we got that point, that's what we've got, okay? And that's all we need to write the equation of the plane. The equation of the plane consists of the conditions on x, y, z that are identical to the condition that x, y, z is in the plane, okay? In other words, x, y, z is in the plane if and only if what? Okay? Well, yep, go ahead.
Is it P cross X, Y, Z?
No. If and only if, this is in the plane if and only if every vector, well, the vector from P to X, Y, Z is in the plane, right? Okay? Otherwise, X, Y, Z isn't in the plane because P is. Okay? And this, of course, occurs if and only if this vector, which we call V, is perpendicular to n. So there's our condition. V from P to x, y, z perpendicular to the normal vector. X, y, z is in the plane if and only if this vector is perpendicular to the normal vector, right? Well, we want to write that as an equation in terms of A, B, C, and x naught, y naught, z naught. So can you write, first of all, the vector V, and then write the condition for V to be perpendicular to n. What's the condition for two vectors to be perpendicular? Dot product is 0. Get used to it. Okay?